Good morning. My name is Haoran. I'm a PhD student, graduated from UIUC recently. And today I'm super happy to share with you our work. Microserve is a system called Microserve, and it's doing power-aware deep learning model serving. And this is a joint work with folks from University of Illinois and IBM Research. I guess you have seen this figure for many times. It's basically showing the trend of computation demand growth of those machine learning models compared to the hardware growth like GPUs and TPUs. And especially after the emergence of large language models and generative AI. And the deep learning demand growth is roughly like 10 times per 18 months. It's much larger than the growth of the hardware accelerators like GPU and TPU devices. And naturally, people have to think about how can we leverage efficiency as the key to further unlock scaling, as mentioned also in the keynote speak this morning. A lot of work has focused on performance efficiency and utilization efficiency. For example, how do we run the workload faster and how to better utilize limited amount of GPU devices, for example. But less attention has been given to the power efficiency or the energy consumption of running those workloads. And in this work, we mainly focus on energy efficiency or power efficiency here, because in the future, those machine learning workloads are likely to dominate the cloud data centers. If you look at the life cycle of large language models, they generally starts from model training or so-called pre-training on massive scales of training data set. And the trained models can be used for inference to serve some applications. But more practically, because of the new training paradigm called pre-training fine-tuning introduced by large language models, a lot of pre-trained models, those are general purpose models, they can be further fine-tuned using domain-specific data set to be some domain expert. And then these trained variants of those models, like fine-tuned LLMs, can be used in various downstream applications, including chatbots, coding assistant, recommenders, etc. And we focus on model serving because model inference and model serving accounts for a much larger portion of the energy consumption or carbon footprint in cloud data centers. For example, Google estimates that in the past 3 years, 40% of the carbon footprint goes to model training, but a larger portion, 60%, goes to model serving. And similarly, at Meta, a paper released from Meta told us that their power capacity breakdown allocates 70% for AI infrastructure used for inference. Before we dive into details, I'd like to very briefly introduce Microserve, which is the first power-aware deep learning model serving system that achieves 1.2 to 2.6 times power saving in various situations while preserving the model serving SLOs. And at the core of this work is to balance the need to meet the performance SLOs and also to minimize the power consumption. So if you look at the model serving system, it usually starts from those trained models. Those ready-to-serve models, they're usually stored in a model registry. And then these models get deployed by this model serving system onto in this case, we consider a homogeneous GPU cluster. And on each node, there can be multiple GPU devices. And the model serving system takes care of those requests from the end users and the applications. What it does is basically two main things. The first is to do model multiplexing, essentially to leverage different sort of model parallelism strategies and do model partitioning and placement of those models onto the GPU devices. And the second thing it does is to do request scheduling, essentially to distribute the requests from the users to different model instances with load balancing, batching, and also deciding the order of the execution. And usually in model serving system, it's first come, first serve, which is a very simple scheduling policy. So you may ask, what are those power saving opportunities? Can we simply reduce the core, like the processor frequency? We did a characterization study to learn about the power saving opportunities by running many different open source LLM models or other machine learning models. And on the right-hand side, on this figure, you can see that there is a roughly linear relationship between the frequency reduction on the x-axis and the power degradation, power consumption reduction on the y-axis. And that's good. But we cannot simply just reduce the frequency without looking at the performance trend. But for the performance trend, if you look at the degradation in terms of the latency, the trend looks quite different in the sense that in the higher ranges of the frequency levels, there's like a relatively less latency degradation compared to the frequency levels at the lower ranges. If you look at the specific model here, GPT-2 large, if we have like a SLO on 1000 milliseconds, without violating this SLO, we get a chance to decrease the frequency from 1.3 gigahertz to 800 megahertz. And that leads to a 44% reduction in power consumption. Actually, this similar results has been observed in production cluster from Microsoft, which is published in a recent paper. But of course, this kind of power saving opportunities vary across different models, and they depend on many factors such as the batch size, output token length, etc. But they roughly indicate that there can be some space for power saving. And let's then look at some challenges here. The first challenge we encounter is that GPU frequency tuning is very coarse-grained. If you look at each GPU device, they can be used to serve multiple models or model partitions. However, the whole GPU device can only be tuned as a whole because they only support coarse-grained frequency tuning, but not per core level frequency tuning. And different model or model partitions have their own characteristics. They also have different SLO requirement, different load patterns. They may also have different sensitivities to frequency scaling. So at the same time, their demand frequency level can be different. And for each model partition, it's already hard to figure out at the runtime what is the optimal frequency to run. As I mentioned, it depends on many factors like the batch size, output token length, the workload right now. And more importantly, the power saving opportunities we found that are limited by the most sensitive partition on the GPU device because each device only supports coarse-grained frequency tuning. And the second challenge we encounter is specifically for large language models because their executions are not deterministic. And this is due to the autoregressive nature of large language models. For those of you who are not familiar with large language models, essentially that means before you execute the request, you don't really know how long it's going to take for you to generate those output tokens. And this is because those output tokens are generated iteratively. In each iteration, we generate one output token, and then this output token is going to be appended to the input sequence. And then these tokens are going through these large language models again to generate the next output token. So this is done iteratively until you reach the end of the sequence token. So what does that mean? We look at a real-world large-scale LLM conversation dataset released by LM6. And we realized that on this figure, you can see the y-axis is the output token length. Both within each model or across different models, the output token length variation is quite high. And current model serving systems only use first come, first serve as a very simple scheduling policy because it works well for those homogeneous, like deterministic executions for most traditional machine learning models like ResNet. But it can lead to headline blocking issues when it comes to LLM executions. And likely there can be SLO violations in terms of the job completion time. So in this simple example, if we don't really know the request output token length, it may encounter this headline blocking in this simple example. But if we know the ground truth length of the output tokens, we can do a better job in scheduling, and that leads to a 40% reduction in job completion time. So essentially, the takeaway here is the power saving opportunities, reducing the frequency without violating the SLOs, are limited by this non-determinism and headline blocking issues. So to tackle those challenges, we also have several observations and some key insights. The first observation we found is the model partitions can have diverse sensitivities. In this simple example, I illustrate on 2 GPU devices. There are multiple models or model partitions, and each block in lighter color means that they are less sensitive to the frequency reduction, and the blocks in darker color basically means that they are more sensitive to frequency reduction. And the root cause of this is essentially in the operator level. You may have different sensitivities in React to the frequency scaling because of different computation intensity. And in this example, if we use this kind of strategy to mix different model partitions with different sensitivities together onto the same device, it's kind of limiting the headroom for you to reduce the frequency. But instead, if you do a very different scheduling strategy to group those model partitions with similar sensitivities together on the same device, you get more chance or headroom for you to reduce the frequency to save power. And here the takeaway essentially is very simple. Power-aware partitioning and placement based on sensitivities can potentially increase the power-saving opportunities. And our second insight is specifically for LLM models. That is, a very small proxy model can understand the verbosity of LLM models. And what does that mean? If we have an LLM model to serve, and the user asks some questions and input queries, and we get some response of some length. But what if we have like a proxy model, somehow before executing this request, we know roughly it's going to output 200 tokens. Then with this information, we can do a better job in scheduling. And we realize that this is achievable by a very small proxy model, for example, BERT-based or BERT-tiny. The intuition behind this is from those input prompt, there can be some hints indicating the output token length roughly. For example, translation basically means that the input query may have the similar output length compared to the output. And the summarization may lead to a much shorter output response compared to the input query. And we found that proxy models can indicate this verbosity so that we can avoid headline blocking and potentially increase the power saving opportunities. With these two insights, it leads to the design of microserve, which is a power-aware deep learning model serving framework, especially for those autoregressive models like LLM models. It basically consists of two phases, an offline phase and an online phase. In the offline phase, it's given the model specifications and the GPU cluster specifications, and we do the profiling of those sensitivity scores of primitive operators defined by the American compilers. And with this sensitivity information, what we're essentially doing is power-aware model partitioning and placement by extending APASO, which is a model parallelism framework. And the central idea of this power-aware partitioning and placement is to cluster those model partitions and operators with similar sensitivities onto the same device so that they can be frequency scaled together. And the output from the offline phase is the model partition and the placement plan. With this plan, we deploy those models onto the GPU cluster. And in the online phase, what we are first doing is to further maximize the power saving opportunities by using the proxy model-based request scheduling. And then we're using dynamic GPU frequency scaler to exploit these created power saving opportunities, reduce the frequency without violating the SLOs. And due to time limit, let's look into the proxy model-based request scheduler in more details. Here, what we are trying to do is to design and train a lightweight predictor that can understand the verbosity of a large language model and estimate the output token length before executing this request onto the model to serve. If we translate the previous example into a workflow when serving those LLMs, it will look like this. We have the end user sending the request to the gateway, triggering the execution of the request on the LLM instance in the GPU cluster. The user sends each input query containing the prompt, and then this input is going to get queued. It may face delays due to headline blocking issues. And then user may be unhappy because of the long response time and until they get the output. But suppose we have an oracle knowing exactly what's the output token length. Then we can leverage this information in the scheduler to do a better job in scheduling, maybe avoid the headline blocking issue, and then the user may be happy because of the shortened response time. So how can we achieve this? Essentially, what we are doing is a prediction-based shorted job first scheduling, using the proxy model as the hint for the estimation of the execution time. And what it takes is the jobs or the requests from the users, and then determine the execution order to execute on the GPU cluster. And this order is based on the output token length prediction from the predictor. Given the model input, we output the predicted length. The reason why we can use the predicted length as the hint for the estimation of the execution time is execution time equal to the constant times plus k times the output token length. The first constant refers to the constant model query overhead and also the prediction overhead from the proxy model, which is deterministic in this case. And the second constant k is the per token generation latency, which is also constant per model instance. To increase the accuracy, we have a semantic cache, which caches the ground truth output token length for every input query. So in the runtime, we don't need to go through the predictor if there's already a cache. Regarding the architecture of the proxy model-based predictor, as I mentioned, we're using BERT as the proxy model. So given the input embedding, we go through the BERT. And then from the BERT embedding, we appended several fully connected neural networks as the predictor to produce the prediction. And the prediction can be some output token length percentile values. These values are from the offline data set on the model history input-output. Here we have a design question, that is to whether we should use simply regression or should we use classification. And for classification, how many classes should we use? And we realize that it depends on the proxy model and the LLM to serve. The rationale here essentially is if we have more number of classes, that leads to very low accuracy because of the harder task. For example, regression is going to have basically infinite number of classes to predict. It's going to be the hardest. So because of the low accuracy, it doesn't really help with scheduling. But on the other hand, if we have less number of classes, for example, binary classification, that leads to worse scheduling as well because the prediction is too coarse-grained. So it doesn't really help with scheduling as well. And in our experiment, we realized that for our LLM models and data, usually 5 and 6 number of classes are the best. In the evaluation, we are interested in several questions. Are the predictors lightweight? Are the predictors useful in scheduling? And how much more power saving opportunities can we gain from the predictors? So to evaluate these 3 questions, we get some V100 GPUs, and then we evaluate several open source LLM models, and also non-autoregressive models, because our work is also a general model, a general framework to support traditional ML models. And for LLM models, we are getting the model input from the LLM-6 chat dataset and the workload patterns from Azure LLM traces. So the first evaluation metric we look at is the job completion time. That is the end-to-end latency for serving those requests on the ML models. And you can find that at varying rates and under different batching strategies in different columns of the figures, we can achieve reduction in job completion time by 33% to 39% compared to the baseline approach. And at varying variations of the workload, we are achieving also reduction in job completion time by 30% to 39%. In terms of the throughput, at varying rates, we are achieving improvement in throughput by up to 3.6 times, and at varying variations, we are achieving the throughput improvement by up to 2.6 times. We also look at the proxy model overhead, because at the end, it's still like we need to meet the latency as a low. We don't want to introduce too much overhead from the proxy models. And on this figure, although it's a log scale figure, but roughly you can see that the yellow part is the model serving duration, where the minimum is 120 milliseconds. But on the other hand, the overhead introduced by the BERT-based proxy model, the average inference latency is 7.6 milliseconds. So essentially, microserve improves the job completion time by 30 to 40%, and the throughput by 2.2 times and to 3.6 times with negligible runtime overhead. So that's good. Because of this improvement in job completion time, we have more headroom to reduce the power consumption without sacrificing the SLO preservations. Although we didn't go into details into the power-aware model partitioning today, but with these 2 phases, offline phase and online phase, we're able to achieve 1.2 to 2.6 higher power saving by dynamic frequency scaling without SLO attainment violations. So in summary, we introduced microserve, which is the first power-aware deep learning model serving system that achieves up to 2.6 times power saving while preserving those request-serving SLOs. And the key idea of microserve is based on 3 points. The first is sensitivity score-based model multiplexing and placement. Basically, we cluster those operators and model partitions with similar sensitivities together onto the same devices. And the second key idea is to use proxy model-based model serving request scheduling to further creating those power saving opportunities. And thirdly, to exploit those created power saving opportunities, we're using dynamic GPU frequency scaling to reduce the frequency as much as possible without violating the SLOs. And that will be all I have today. Thank you so much for listening, and I'm happy to take any questions.